Direction ratios. Welcome, everyone. Let's begin our new session on direction ratios. Now, before we dive into today's main topic, let's take a moment to reflect on what we covered in our previous subsection. We explored the concept of direction cosines, which, as you remember, are simply the cosines of the angles that a vector makes with each of the three coordinate axes. Now, while direction cosines are mathematically elegant and very precise, they do come with a certain limitation. They are constrained. Because they are cosine values, their values are always restricted to the range between -1 and +1. This can sometimes make our algebraic manipulations a bit more cumbersome. So, to make our lives a little easier and to simplify our future calculations, we are going to introduce a new concept today: direction ratios. We'll see how these provide us with a much more flexible way to describe the orientation of a vector. Understanding the concept. To start, let's consider a position vector, r vector, of a point P with coordinates x, y, and z, located in our three-dimensional space. The magnitude, or the length of this vector, is denoted by r, which is the magnitude of the r vector. Now, if we recall our previous study on direction cosines, we already know the relationship between these coordinates and the angles the vector makes with the axes. Specifically, L, which is the cosine of alpha, is equal to x divided by r. M, which is the cosine of beta, is equal to y divided by r. And n, which is the cosine of gamma, is equal to z divided by r. Here is the key part. If we rearrange these equations to solve for our coordinates, x, y, and z, we find that x equals r times L, y equals r times m, and z equals r times n. Notice that these resulting values, r times L, r times m, and r times n, represent the components of our vector along the x, y, and z axes. Because these components are simply the direction cosines multiplied by a common factor, r, we can say that these components are proportional to the direction cosines L, m, and n. It is precisely these proportional values that we call the direction ratios of our vector r. This leads us directly into our formal definition on the next slide. Now that we've established why we need a more flexible alternative to direction cosines, let's dive into the mechanics of how this works. Formal definition. Now that we've seen how the components of a vector are related to the direction cosines, let's move on to the formal definition of direction ratios. Essentially, the direction ratios of a vector are any three numbers. Let's call them a, b, and c that are proportional to the direction cosines L, m, and n of that same vector. To put this into mathematical terms, if L, m, and n are our direction cosines, then the ratio of L over a, m over b, and n over c must all be equal to the same constant, which we will denote as k. This constant k is what links the two sets of numbers together. Now, here is a very useful practical application you'll see often. Quite commonly, we can simply use the coordinates of a point P, which are x, y, and z, as the direction ratios for the position vector r, which is the vector from the origin O to point P. So, in this specific case, we can simply say that a equals x, b equals y, and c equals z. This makes working with vectors much more intuitive, as we can use the coordinates themselves to represent the direction. In the next slide, we will look at how we can use these ratios to actually calculate the direction cosines. Relationship between direction cosines and direction ratios. Now that we understand that direction ratios are simply proportional values, you might be wondering, if they can be any numbers, how do we get back to the precise direction cosines we studied earlier? This brings us to the relationship between the two. You see, while direction ratios can be any real numbers, they can be huge or tiny. Direction cosines are normalized. This means they are scaled specifically so that the sum of their squares always equals 1. So, if you are given a set of direction ratios, let's call them a b and c, you can find the corresponding direction cosines, L, m, and n, by following a simple two-step process. Step 1, you need to calculate the magnitude of these ratios. To do this, you take the square root of a squared plus b squared plus c squared. Think of this as finding the length of the vector formed by these ratios. Step 2. Once you have that magnitude, you simply divide each of your original ratios by this value. So, L equals a divided by the square root of a squared plus b squared plus c squared. M equals b divided by that same square root, and n equals c divided by that same square root. By doing this, you are essentially shrinking or stretching your ratios so that they fit the required scale of direction cosines. We will see this exact process in action in our next slide with a practical example. Real-world analogy. Imagine you are trying to guide a friend through a dense forest to find a hidden treasure. If you were using direction cosines, it would be like giving them a very precise compass bearing. You might say, walk exactly 30 degrees northeast. Now, this is incredibly accurate, but as we discussed in the previous slides, it requires dealing with trigonometric values and angles, which can get quite complicated as you move through three-dimensional space. On the other hand, using direction ratios is like giving them a set of relative steps. You might say, walk 3 steps east, 4 steps north, and then climb 5 steps up a ladder. Notice that I haven't mentioned any angles here. I've simply given you 3 numbers that represent a movement in each direction. The key takeaway here is that even though these 2 methods look different, they describe the exact same path. The relative steps of the direction ratios are much easier to communicate and much simpler to use in your calculations, yet they still point you toward the same destination as the compass bearing of the direction cosines. Now, before we dive into the formal calculations and examples, I want to take a moment to step away from the formulas and look at a real-world analogy. This will help you intuitively grasp why we even bother with direction ratios instead of just sticking to direction cosines. In the next slide, we will see how this concept of relative steps works in a concrete mathematical problem. Illustrative example. Now that we have understood the theory and the relationship between these 2 concepts, let's put everything into practice with an illustrative example. Here is our problem. We need to find the direction cosines of a vector, given that its direction ratios are 2, -3, and 6. Let's walk through the solution step by step. In step 1, we simply identify our given values. From the problem statement, we have A equals 2, B equals -3, and C equals 6. Next, in step 2, we need to find the magnitude of these ratios. This is a crucial step we discussed in the previous slide. We take the square root of a squared plus b squared plus c squared. Plugging in our numbers, we get the square root of 2 squared plus -3 squared plus 6 squared. When we calculate the squares, we get the square root of 4 plus 9 plus 36. Adding those together gives us the square root of 49, and since the square root of 49 is 7, our magnitude is 7. Finally, in step 3, we apply the formula for direction cosines that we learned earlier. We divide each of our original direction ratios by this magnitude, which is 7. So, L equals A over 7, which gives us 2 over 7. Then, M equals B over 7, which gives us -3 over 7. And lastly, N equals C over 7, which gives us 6 over 7. Therefore, our final answer is that the direction cosines are 2 over 7, -3 over 7, and 6 over 7. Notice how the direction cosines are all within the range of -1 to 1, just as we expected from our earlier discussion. Now, let's quickly summarize the key takeaways from this entire lesson. Key takeaways. First, let's revisit the core definition. Direction ratios, which we denote as A, B, and C, are simply any 3 numbers that are proportional to the direction cosines, L, M, and N. This means they point in the same direction, even if their magnitudes are different. Second, remember the connection to coordinates. As we saw in our derivation earlier, if you have a position vector r that ends at a point P with coordinates x, y, and z, you can actually use those coordinates x, y, and z themselves as your direction ratios. It's a very convenient shortcut. Third, let's summarize the conversion process. If you are given direction ratios and need to find the direction cosines, the procedure is straightforward. You just take each ratio and divide it by the square root of a squared plus b squared plus c squared. This process, which we call normalization, scales the ratios down to the required magnitude. Finally, I want to highlight the main advantage of using direction ratios: their flexibility. Unlike direction cosines, which are strictly constrained to values between -1 and +1, direction ratios can be any real numbers you like. This freedom makes them much easier to work with in complex 3D geometry problems. All right, we have covered a lot of ground today, so let's take a moment to recap the key takeaways from this lesson to ensure everything is clear before we move on to some common pitfalls. Now, before we wrap up, let's look at some common mistakes students make, so you can avoid them in your upcoming assignments. Common mistakes. First, a very common mistake is confusing direction ratios with direction cosines. It is easy to mix them up because they are so closely related. However, always remember this fundamental rule. Direction cosines are normalized, meaning the sum of their squares, L squared plus M squared plus N squared, must always equal 1. Direction ratios, on the other hand, are much more flexible. They can be any real numbers and do not have this restriction of summing to 1. Second, please be extremely careful with sign errors. When you are performing the conversion process we discussed in the previous slides, specifically when you are calculating direction cosines from ratios, ensure that the sign, whether it is positive or negative, is preserved. If a direction ratio is negative, its corresponding direction cosine must also be negative. Finally, watch out for errors in normalization. A frequent mistake is simply forgetting the final step of the calculation. You must divide each individual ratio by the magnitude, which is the square root of a squared plus b squared plus c squared. Without this division, you haven't actually found the direction cosines, you've only found a set of proportional values. Now, as we wrap up our lesson, I want to draw your attention to this final slide, which highlights some common pitfalls you might encounter when working with these concepts. It is crucial to keep these in mind to avoid losing marks in your exams. Keep these points in mind, and you will master this topic with much greater accuracy.